Hi everyone! In this video I will show you how to derive the single particle Maxwell-Boltzmann distribution for an ideal gas. I will do this in one dimension only. Once you see the derivation in one dimension, it is trivial to do it in arbitrary dimensions. To do this, we only need to make one assumption, and that is that every state the system can be in is equally likely when the system is in equilibrium. So first, what do I mean by state? A state of a system is just a set of variables that describe that system. In the case of the ideal gas, the state is merely the set of positions and velocities of all particles. Next, what do I mean by equilibrium? This one is more subtle, but not hard to understand. Let me first give you an example of a system that is not in equilibrium. I will do this for two dimensions. Consider all particles of a system to be localized in some region. We don't need to know their exact state, we just need to know that they're localized. Now, what happens to the particles a short time later? Well, depending on their exact state, their distribution might become something like this, or it might end up looking like this. But if their energy is finite, which is an implicit assumption here, we will never find them in this distribution, or this one, or this one. The reason for this is simple. Even if all the particles in the initial state have velocities pointing in just the right direction, they won't have enough speed to get to this state if delta t is small enough. However, if we let the system evolve long enough, the probability for any state will approach a constant. The time to reach an equilibrium is called a correlation time. It is the time for a correlation between any two variables, say v1 and v2, to become negligible. So, for a system to be in equilibrium, we must either wait a while, or we must be completely ignorant about its initial state. Okay, so now that we understand the necessary assumption and the condition under which it's true, we can go ahead and derive the single particle distribution. The procedure is very simple. We just write down the probability density for a state, which, as we said, is a constant. The probability itself is this constant multiplied by the infinitesimal phase space volume. However, we must remember that the system's energy is conserved, so the particle speeds must be constrained by the Dirac delta function. Before we can obtain a single particle distribution, we need to know what this constant is. Since we are dealing with a probability, integrating it over all variables must equal to 1. L here is just the size of our one-dimensional box. The integral over the particle positions is trivial. The integral over the velocities can be expressed in spherical coordinates. d omega here is the solid angle in n dimensions. For now, we'll just call this whole thing omega sub n. V is the radius of the n-dimensional sphere, so this term here is just v squared. We can use this property of the delta function to write our delta function like this. So finally we have and solving for n script, we obtain this answer. Now we want to integrate over all but one particle velocity, say v1. We already know the integration over x gives L to the nth power, so we can write it directly. Since v1 is a free parameter, not an integration variable, we can combine it with the total energy. And let's call this term E prime. Now notice that this integral is identical to the one we have already done, but for n-1 particles. So all we have to do is take our previous result and let n go to n-1 and e go to E prime in this box. Let's look at this term and factor out e. I've also split this term into two. We can actually relate the total energy E to the particle number n. Since the total energy has to be conserved, we know that regardless of the state, this equation will always be true. So if we take the expectation of both sides, and since all the particles are the same, this term becomes n times the average kinetic energy per particle. So we can write E equals n times k. Plugging this result into our expression, we get this. Now, if we have a large number of particles, in other words, if n goes to infinity, we can take the following limits. So we got our exponential term here. But we still have to deal with the normalization factors and make sure they approach something finite as n goes to infinity. Let's plug in the result for n script and see what we get. We can cancel some terms and rearrange others to make it nicer. So the final thing to deal with is this ratio of omegas. Recall our definition of omega, which is just the integral over the solid angle in k dimensions. I will not go into details of how to compute this here. We can just look this up on Wikipedia. The answer is this. So this ratio equals to... Again, I'm not going to prove this, but the limit of this ratio as n goes to infinity is this. You can put it into Mathematica and check. Plugging this into our expression, we see that n cancels out, leaving just this. If we call this ratio sigma squared, we can write the exponent like this, which makes our probability a normal distribution. We can relate K, the kinetic energy per particle, to the temperature. This is exactly the relation for an ideal gas in one dimension. For 3 dimensions, we would find that K equals to 3/2 kBt. So that's it. That's how you derive the Maxwell-Boltzmann distribution. If you want me to make a follow-up video on how to derive the n-particle distribution in the presence of a heat bath, drop me a comment and subscribe. Cheers!